Happy Friday. It's January the 29th, and we'll be talking about orbits today. Yes, so topics we're covering today. We just decided that we're going to do team presentations on your updated mission, payload requirements, and your decided orbit after lecture today. The lecture will consist of Newton's laws, Kepler's laws, trajectory types, coordinate systems, orbital elements, and orbit types, and then why spacecraft use certain orbits. So at the very core of orbits is Newtonian mechanics. Newton's laws of motion and Newton's law of universal gravitation underpin the way spacecraft move around planets, the way planets orbit our sun, and on to larger celestial bodies and systems. Hopefully you all know Newton's laws of motion, as you all are upperclassmen. Regardless of the major you're in, you're still in STEM. And here's a reminder, we just covered this last time, Newton's law of universal gravitation. This is the slide that we saw where the phenomenon that we were exploring was gravity. You'll see that there are expressions for gravitational force, the velocity of a spacecraft in circular orbit, and a spacecraft's orbital period. The new stuff that we're covering today are Kepler's laws of planetary motion. So to be more specific about orbits, we need to break down each of these laws. Kepler arrived at these laws by trial and error and some vague notions about celestial harmonies. Kepler's laws only describe the motions without explaining why they move that way. Newton provides the explanation. Kepler's laws are a natural consequence of Newton's 3 laws of motion and his law of universal gravitation. By addressing the why, Newton gave his laws predictive power that allows us to use them as tools to explore the universe, both figuratively and literally. We can predict new phenomena or understand oddities in the motions, as the laws give us a framework in which to interpret the data. And we can literally use them to fly spacecraft through our solar system. So both astronomers and spacecraft engineers should understand orbits. So the first law of orbital motion, it's visually depicted on the right here, where the shape of an orbit is a conic section with the center of mass at one focus. So you can take a cone and you can cut it in any place in a plane, and that will signify a type of orbit. There are 2 parts to Newton's formulation of Kepler's first law. So the shapes of orbits we just saw, curves are found by cutting a cone, and these shapes are circles, ellipses, parabolas, and hyperbolas. And you'll notice that the center is the foci, or the focus. Strictly speaking, it is not just the Earth orbiting the sun and the Earth and the sun orbit together. So the center of mass the center of mass is not in the center of the sun. It is just slightly displaced depending on the mass distribution of the 2 bodies. The second law of orbital motion is that orbital motions conserve angular momentum. You can see this visually depicted as in a spacecraft sweeping in an orbit will cover the same area over the same amount of time. Angular momentum is defined by mass times speed times the distance from the center of mass. And that value, angular momentum, will be constant throughout the entire orbit. The third law of orbital motion is this relationship between the period of an orbit and the semi-major axis of the orbit. If these coefficients, which are, you already know pi, you know the gravitational constant, and then we have the mass of the first body and the mass of the second body, where the mass of the first body can be the sun or a planet, and the mass of the second body could be a spacecraft or a planet. So those things stay constant in an orbit, and you'll notice that it's P, the period of the orbit, and A, the semi-major axis of the orbit, that are really dictated by each other. So those can change. You'll see this relationship play out with all of the different planets in our solar system. So if we were to plot the square of orbital period for all the planets, it directly corresponds to a linear relationship with the cubed of the semi-major axes. Okay, so let's go back to the conic sections and the type of orbits that you can see. Orbits are strictly closed. So for the open orbits, we call them trajectories. So to be more general, we have a suite of trajectories. There are two different velocities that are important to know when defining what orbit you have. So the first one is a circular orbit velocity. So this velocity dictates the boundary of a body that is traveling in an ellipse or a circle. So we'll see here that if your satellite travels less than the velocity necessary for a circular orbit, then you're traveling in an ellipse. And then it's self-explanatory, but when your velocity is at the circular orbit velocity, then you're traveling in a circular orbit. The second velocity that you need to know about is something called an escape velocity, which is defined here. So the escape velocity will give you a parabolic motion where you just meet the criteria for escaping the potential well of the body you're orbiting. If you're somewhere in between that circular velocity and the escape velocity, then you're going to be traveling in ellipse. If you're traveling faster than the escape velocity, then you'll travel in a hyperbola. To give you some estimates or approximations of these values, at Earth's surface, the circular velocity would be 7.9 kilometers per second. The escape velocity for Earth, if you're trying to escape from Earth's surface, is 11.2 kilometers per second. And that's kilometers per second. It is extremely, extremely fast. Next, we'll talk about coordinate systems. Coordinate systems are important for attitude determination and control maneuvers, like pointing, but also its sister field, the guidance, navigation, and control subsystem for propulsive maneuvers. You want to know how you're pointing when you fire a jet engine or a rocket thruster, because that direction matters when you're changing orbits. So we use different coordinate systems for convenience, like if there's something to reference in that coordinate system that makes sense for that mission. So now we're going to do a little exercise. I want you to make this shape with your hand. You should recognize it as the right hand rule. But if you make these three orthogonal directions, just hold it out. You just made a coordinate system with this gesture. Now, if you change the orientation of your hand, that also is a coordinate system. There are endless possibilities for what could be a coordinate system, but there is a small set of coordinate systems that are actually useful for spacecraft. The 5 steps in specifying a coordinate system is picking the origin, so that's where the 3 vectors intersect. Pick the fundamental plane. So let's say that I care about pointing directly at the camera. So my plane will be like this, vertical up and down and straight into the camera. And then the perpendicular vector will be my middle finger, which is going to my left. And then you can pick a principal direction. And since I care about looking into the camera, I'll just say that my index finger is that principal direction. Yeah, coordinate systems, not so hard. Now let's talk about specific coordinate systems that seem to be useful for spacecraft. The heliocentric ecliptic coordinate system is a celestial coordinate system commonly used for representing the apparent positions and orbits of solar system objects. Because most planets, except for Mercury, and many small solar system bodies have orbits with only slight inclinations to the ecliptic, using it as the fundamental plane is convenient. The system's origin can be the center of either the Sun or Earth. Its primary direction is towards the vernal or March equinox, and it has a right-hand convention. This orbit is particularly useful when you are traveling through the solar system to another planet. The geocentric equatorial coordinate system, otherwise known as the Earth-centered inertial or ECI frame, has the origin at the center of mass of Earth and are fixed with respect to the stars. So these directions, these vectors in the coordinate system stay static even though the Earth's surface is moving. And they stay static with respect to the celestial sphere. You can think of it as reference stars in the celestial sky. So for objects in space, the equations of motion that describe orbital motion are simpler in a non-rotating frame, such as the Earth-centered inertial frame. And this is because we take equations of motion in an inertial frame. We don't like to define motion for frames that are accelerating, which includes translational acceleration or rotational acceleration, which is what the Earth is doing. The ECI frame is also useful for specifying the direction towards celestial objects. Now, if we were to spin with the surface of the Earth, then we could define something called the geographic coordinate system or the Earth-centered, Earth-fixed coordinate system. GCS can give positions as spherical coordinate systems using latitude, longitude, and elevation, which many geographers find useful. As they could also give you coordinates as to Cartesian coordinates in 3 space, so maybe X, Y, and Z, or as a set of numbers and letters forming a geocode. This is something that GPS satellites can use, or what you can reference to on your phone, for example. To represent the positions and velocities of terrestrial objects, it's convenient to use ECF coordinates, or latitude, longitude, and altitude. The right ascension declination coordinate system should be familiar for our astronomers in the class. Right ascension and declination are just numbers like latitude and longitude, except applied to the stars. This coordinate system is used in astronomy for celestial observations. And then finally, there's something called the parafocal coordinate system, which is very convenient when determining the orbital trajectory. So you can see here that there's an elliptical area that is defined where the boundary is that orbital trajectory. The angular momentum of this disk is coming out of the plane. And if you look directly down that angular momentum vector, you can see a radial vector and some angle associated with where a spacecraft or satellite is in that orbit. So this is a really convenient coordinate system for simulating the dynamics, simulating the equations of motion of a spacecraft in an orbit, a closed orbit. So then how do you represent an orbit? In the parafocal plane, we can define orbital parameters. The first 5 classical orbital elements, semi-major axis to argument of periapsis, defines the shape of an orbit. And that last parameter, the time of periapsis, tells you where in the orbit the spacecraft is. So let's just go through these different orbital parameters and see how they relate in this visual representation. So we've got the semi-major axis, which defines the size of the orbit. It's usually measured in altitude, so kilometers or meters. The eccentricity defines the shape of the conic orbit, so how the semi-major and the semi-minor axes, which is this is the semi-minor if it's shorter than this direction of the orbit. So circular orbits, the semi-major axis is constant throughout the orbit. For eccentric orbits, then you'll find that there is going to be a squat point to the orbit and a longer, wider part to the orbit. Inclination defines the tilt of the orbital plane with respect to the fundamental plane, or this gray disk is the fundamental plane. So I is right there, the angle between those two planes. Although mathematically it is the angle between the spin axis and the angular momentum angle of the orbital plane, where this directly up is the spin axis and the angular momentum vector is that perpendicular to the orbital plane. Right ascension of the ascending node defines the swivel of the conic orbit with respect to the fundamental plane. So it's this green symbol right here. And then the argument of periapsis defines the orientation of the orbit with the orbital plane. So it's this purple parameter right here. And you can see how if that angle were different, it would skew the orbit along this plane. Yeah, okay, I hope that visual representation helps. And then finally, the time of periapsis shows where the spacecraft is within this orbit, and it's measured from the argument of periapsis, or where that 0-degree angle reference marker could be if you were looking at a unit circle, for example. I will note that the true anomaly is undefined for circular orbits because that argument of periapsis is undefined if you don't have a strict semi-major axis. Okay, orbital elements are typically represented in something called the NORAD two-line element, or TLEs. The orbit data can be extracted from this representation of data, where these numbers have inside epoch, so the time, eccentricity, which we just talked about. For this orbit, it looks very circular. Inclination, perigee, apogee, and all the other classical orbital elements that we talked about. And I want you to just pause for a moment and guess which orbit this is, what spacecraft body. Maybe there are some clues from these diagrams, but this is the ISS orbit. So you'll notice that its perigee, its minimum height in orbit, is 418 kilometers. Its apogee, which is the farthest point it is away from Earth, is 421 kilometers. Its inclination is 51 degrees. Our Earth's fundamental plane is at the equator, so that's the angle from the equator. Yeah, and in this particular instance, its argument of perigee is 309 degrees along the orbit. What else do I want to say? There are 15 revolutions per day, which is about 90 minutes per orbit. Yeah, that's all I want to say. Okay, so the effect of a launch site on inclination. Where you launch your rocket from can define the inclination that you'll see for your orbit. But also, if you don't want to be in that orbit, it defines the amount of rocket fuel you need to bring so that you can change your inclination away from where you just launched from. It's very advantageous for you to launch near the inclination of the orbit that you ultimately want to see. And I'll just note that Hawaii is the closest US state to the equator. So it's very advantageous for us if we were to launch something from Hawaii to go into an equatorial orbit, for example. That's why different space agencies or teams will send their spacecraft to specific launch sites so that they can get that advantage. Oh, now why do you want to go to an equatorial orbit? That's where a lot of communication satellites go in an orbit called the geostationary satellite orbit. Okay, and this is a really big slide. So there are a ton of different orbit types. Let's just focus on these larger categories first. There are geocentric orbits. So let's break down that word. Geo for Earth, centric as it's centered. And these orbits just toggle the altitude of spacecraft orbiting around Earth. The low Earth orbit, ISS, is in a LEO. Let's see, we just talked about geostationary, that's another geocentric. There's also mid-Earth orbit, somewhere between low Earth and high Earth. There are different inclinations. So we just talked about equatorial orbits, where you're 0 degrees away from the equator, but there are also polar orbits in which you're 90 degrees. So you're orbiting orthogonal to the equator, and you're passing over the North Pole and the South Pole. So those are two extremes. And then remember, in the demo that Miguel showed us, the inclination affects the kind of latitudes that we see. So for the ISS, if it was at 51 degrees, you're limited to, remember, not seeing the Alaska glaciers, for example. So inclination toggles the amount that you can see over your ground passes. There are directional classifications. So in an orbit, say you have this orbit, you can either go this way or you can go the other way. So there's something called retrograde and prograde. For eccentricity, there are the extremes of having a circular orbit, which is 0 eccentricity. And then there are very eccentric, where you have a spacecraft body and your apogee could be really far off, but your perigee is really close to the planet. So you'll linger a lot at apogee, and then you'll swish really quickly around perigee, and then you'll come back to apogee, stay there for a while. There are also different synchronous orbits, where you can synchronize with the motion of the sun or synchronize with the motion of Earth, so that you're always looking at a certain place on the Earth. And then what else? There are special classifications. I mean, there are a ton of different orbits with specific orbital element definitions that, you know, it's a whole field in itself. For missions, there are orbital mechanics specialists who do a lot of simulations where they try to plan flybys of a lot of different solar system bodies to get to, say, an outer planet with the minimum amount of delta V, which is, delta V is the difference in velocity, and it's how we measure the amount of fuel that we bring with us into space. So yeah, maybe some notable orbits. There's something called a graveyard orbit, which is just beyond geostationary orbit. Because communication satellites are so far away, to dispose of them, to have the end of life mission, you need to allocate an orbit for them to be discarded. So the geostationary satellites will have a little bit of reserve fuel left so that it can boost its altitude to this graveyard orbit, where it can rest in peace. Yeah. It's a big field, so I'll let you explore it yourself. Maybe we can talk more about it in the latter half of the semester, but I think for the purpose of this mission that you're designing, we've covered the range that you should care about. Okay, so there are some questions. The effects of other planetary bodies are relatively small for a satellite orbiting the Earth. Doesn't the moon slowly affect the orbit? So yes, there are many different perturbations on satellite bodies. I mean, you can integrate all of the perturbations or small orbital effects from all the bodies in the universe. The moon is certainly the closest one, so it would give you the most perturbation or unwanted disturbance in your orbit. So yes, it's true, but for many missions, this is not significant enough to really impact the mission. Some spacecraft bring fuel with them to do what they call station keeping, which is if there is a perturbation, it can be compensated for with a little thrust. And then SSO eclipse seasons. Could you also tweak the orbit to stay in the sun when the seasons change? Yes, absolutely. So there is one way of getting around eclipses. You can orbit the Earth in such a way that you are never out of the sun. So let's say the sun is over here and the Earth is here. You can orbit in a polar orbit such that you never go behind the Earth, or you never go behind the line of sight between the Earth and the sun. So you can have a polar orbit. You could also orbit with the Earth and never leave sight of the sun. So yeah, there are those types of orbits that you could pursue. Okay, I think I'm done with my lecture today.